seems like that the recording is going. So I need to record this, so also later some of you who do not join online can look at it. I'm really happy that you're on the path of covering this material. So today we're going to look at the HDBSCAN model, not the model, but the clustering algorithm, and that is actually also a model. So I mean, like, we'll briefly talk and maybe even try to implement something in regards to classifying things or segmenting things or doing a lot of data related tasks just using clustering. That was approach that usually scientists or data scientists took like before the advent of deep learning, like probably when around like 2000s and 90s, there was a lot of things going on with the clustering and decision trees and all sorts of those things. But this is very related to deep metric learning that we started working with contrastive loss model that we all built like a few sessions ago, and then we moved to the PCA, principal component analysis, to decompose and reduce dimensionality, so that we have not like 128 dimensional vectors, but at the end two-dimensional vectors, like in this picture where we can see it. Like the data points clustered nicely together. And if that would be 128 dimensions, then we would need to use something like, so I don't know, like even with the other dimension reduction algorithms, they will still not represent the real data distribution. It's not possible visually to demonstrate it. The best you can do is probably use some kind of 3D more visualizations, but that is again reduced to the 3 dimensionals. So the tensor board is nice thing. The same you could do with, for example, image segmentation. If you have like cartoon characters and we cluster together pixels that are similar, and you'll see that, for example, the cartoon character is one group of pixels and all the background is other group. And we did this just by using clustering without any deep learning. And if you can imagine, if you give like the whole set of images from the cartoon, like hundreds or thousands of them, and then just segment out, use that clustering material, and then use that only on one frame, you would get even better clustering properties. So now deep learning is not always the answer. Many times also these kind of algorithmic mathematical ways work more robust and better. So we'll look at one of really exciting clustering algorithms. There are not that many like classical approaches that are still developing at this stage. So there are some. Probably you have heard about the team sort, for example. That was one of the latest additions to sorting algorithms. Like I think it was 2005 or something like that. And the HDBSCAN and the DBSCAN and optics and all sorts of density-based clustering algorithms are also like quite recent. I think this paper, I can double check what year it was. So I will reshare my screen, check that I shared the Safari. And the HDBSCAN paper, I think it's, if I'm not mistaken, it's not actually that long ago. I think it is 2017 or something like that. And the implementation that we will try today, it's also not, I think, from the original authors, but the blog and the documentation that I referenced in the material is really nicely laid. At the same time, there are some things that are maybe not understandable directly immediately. So I will try to keep short. At the same time, if you have some questions, ask me. This is, I think, really exciting because there are multiple things inside that clustering algorithm that is connected to the deep metric learning and all sorts of embedding type of things that are like quite like important for future of deep learning in general, for this hidden state, like whenever you you learn and then do the transfer learning, or you do the one-shot learning, zero-shot learning. So anyways, let's keep digging in. So the algorithm itself relies on something called, they have the what's the name, they have some specific way, their own metric for the distances. We'll cover that just in a second. I think there was a name for that. I kind of forgot it in a second. I'll just check me. I will check. Maybe I think it was all lambda. Yeah, I think it's lambda distance was called or something. Even though lambda is not a good name for anything regards to distances, because in mathematics you have lambda expressions, and this is not what you want to associate this. But anyway, so I will start copying some of the equations. So they do not use the Euclidean distance. So that is the first thing. So you can use also your own distance metrics. This is not like precisely defined. So the algorithm starts by using their own distance metric. So what I mean by this is that you have 2 points, and we will cover this just in a second. So let's say we have not 2 points, but 3 points. So there is a point, there is a B point, and let's say there will be some kind of C point. And the distance of Euclidean distance or cosine distance that we already covered, that is easily the shortest distance or the shortest angle or whatever. But this distance metric is one of the first I think we covered that is a little bit more interesting. So it used the maximum of 3 types of distances. So, and the last one, D, is either Euclidean, cosine, or something that we already know. So this will be maximum of, let's say, Euclidean here, and the core distance of k here and here. This is something that they invented themselves, and you choose the maximum value of 3 of those. And this is also called mutual reachability distance. So mutual reachability distance, and this is because it's calculated from both sides. If you look at the core distance equations, so they do not take in A and B together. They just look at A and they just look at B and give out the value that then you can get from the maximum equation here. And the way how this happens, it's really interesting. This is the same authors also a few years before published DBSCAN without the H in front. I think if you look at what is the full name of that HDBSCAN, let me try to check. So there is density. So the first one, DBSCAN, means density-based spatial clustering applications with noise. A lot of words. So just a second, maybe I should pick that up as well. I will drop that in the first slide. So that was the DBSCAN, the first algorithm. And I will just in a second explain what is the difference. There's actually quite a few really clever ways that they applied even in the first algorithm and also in the second, the same authors. So this is a DBSCAN density-based spatial clustering applications with noise, and H, I think it was hierarchical, if I'm not mistaken, but I need to double check myself. So kind of was not thinking about the names before. I'm just using this clustering technique quite often, but I never actually looked what is the H in front. I think it should be hierarchical. If somebody can confirm my suspicion, can write in the chat. Where was the paper? I just found the paper and then I closed it. Yeah, it's hierarchical, right? That is what I expected, because the algorithm itself, when we look at it just in a second, you will see it is related to hierarchy, and the previous one is a little bit more simpler. So let me copy. So this was the first one and the second one. The one thing that you already see, there is a density base. So the density, when you see words density, it means that first of all, this is probably related to density probability distributions, would you basically, and the density you can also interpret if you look at this image. There are some clusters that are dense, like a lot of well, like data points clustered together with some kind of close distances, and then there are some sparse clusters like this one. And this is not bad or good, it is. So some data points might be related with with the metric that is a little bit sparse, and other ones could be like closely densely. And by the way, there is also a very interesting factor. If you start working with the synthetic data sets, then often we don't see any of these issues at all. When you start working with the real data sets that's coming from nature, or like measurements or something, then this is very common that they are not like clustered very nicely, in the sense that the all samples, the distances between all samples are the same. They are more like distant. Some are sparse and some are dense. That's why these are also very good. So returning back to the mutual reachability distance metric. So this metric is defined by an algorithm, but I remember that we are working with deep metric learning. So the other models that we will look later, and we already looked at the contrastive loss, means that you can learn also this metrics. This is not always this does not always need to be an algorithm, but I think this is a great example where the classical programming approaches still show really good potential when you just invent your own algorithm that is applicable for solving very hard problems without machine learning. So anyways, the way how this goes for the HDB version is that you need some kind of hyperparameter, and your hyperparameter or your heuristic or your like yeah, your hyperparameter in this case is the k. So, and this k is actually not the number of clusters, but number of samples in neighborhood that you want to look at. So the number of samples that you consider is the similar density. You don't need to know what is the distances between those samples. You just say, I would like to look at neighborhoods with 5 samples, and I want to see, like, automatically calculate what would be the approximate distance between those 5 samples. So hyperparameter, in this case k, which is the mean samples in neighborhood, samples in neighborhood, probably need to double check that syntax. I'm not a native speaker, as you know, but I guess kind of, did I got it right? Okay, the hood too. Okay, that is our hyperparameter here. All of these clustering algorithms have hyperparameters, like even those which have very little. So this one is very nice because you don't need to know the k, how many clusters there will be. Like in this first sample, this is one of the most powerful features for this kind of algorithm. You don't need to say that here are 1, 2, 3, 4, 5, 6 clusters. It automatically can understand that there will be 6 clusters. But like if you would use k-means, first of all, the output will be terrible. Second of all, you need to know how many clusters you have. And third of all, it cannot detect the noise. So this one is able even to filtrate out noise. That is, again, quite cool feature that you think about. If you feed this HDBSCAN algorithm spectra of audio, you could probably try to separate noise just by using the clustering techniques, which is, if you think about really powerful approaches, you can do with this a lot of things actually. So anyways, the returning back to here, the hyperparameter is minimal samples in the neighborhood. So this is better, I think, than knowing the number of clusters. Because, for example, if you have like a lot of photos of different people and you don't know how many people are there, you just know that there are people, and maybe then this kind of mean samples in a cluster could be a measure, like how many you guess how many samples of photos of each person you have in the dataset. You have a guess, let's say that there should be at least three photos unique for each person, and if if you have that assumption, that hyperparameter, you're good to go. So that's really nice feature. So again, I'm just like a little bit chaotic maybe, but I'm trying to cover some of the basics. So again, return here. So we have three parts. We have this Euclidean or cosine or something that we already know with those 2 points, and then these core metrics and the core distance. So core distance in this case is calculated by having they just take the each of the samples and then calculate what are the first 5 closest other samples, because you say that k is 5 in this case. So in this case, k is 5, and you go over each of those samples actually, and then you measure like the 5th closest sample distance is this radius here. So this is our reference distance for the point A, and we do the same for the point B, and we get the other distance. And that distance here, again, it could be Euclidean cosine or whatever, but again, this is not direct distance between the A and B, but this is just the neighborhood distance of the 5 closest samples, and then that of the 5 which is the farther away. So that's the way how you calculate that other distance. Let me check. There were, I think, more pictures that we can talk about a little bit. Yeah, there was another example that is really nice, where you can see the why this matters. So, for example, you have the 2 points in a configuration like this, where there is a green circle and a blue circle, and these circles are calculated by that K5 method. Of course, you can choose like three closest neighbors, 5, 10, 12, like 10, 20, whatever, like it doesn't matter. Like actually, the more closest neighbors you take, the more robust will be the output. If you just take the let's say first 2 or just the first closest sample, then that will fluctuate a lot. So the distances will be not so stable. The more you take, the more like kind of real density you measure. So in this case, what I mean, why this sample is very good, is that you see there is a green, for example, this will be core distance A, and the blue will be core distance B, and the Euclidean distance will be between those 2 points here in the middle, right? And you can easily see that the biggest distance will be the green one, and that this is the max distance of that A point. And this is because the density of that neighborhood is very low, so it's very sparse. Around that point we have very sparse other points, and in that way we kind of got that the distance between that A and B is that sparse distance around that point. So that's really interesting way to measure the distances between the points. If you think about it, there are some caveats as well, but in general, really interesting approach. So that's one. The other thing is, so yeah, so the other thing is that that the this is a HDBSCAN approach. So the HDBSCAN works with the K so this hyperparameter is the k closest neighborhood samples, and then that's the way how you calculate the distance between those samples, either using those k closest samples, where of course yeah, and or using the maximum of the like Euclidean pairwise distances. That's one. Then the simple DBSCAN that is also actually included in HDBSCAN, you will see in a second, um, is using something a little bit different. So the instead of h instead of k num samples closest samples, it uses the epsilon, if I remember correctly, epsilon constant. And this is again really interesting and clever approach how to calculate the distance metric. I will quickly try to find image how it looks like. Hopefully this kind of lets you start thinking about the way like that the distances between two data points not always can be just expressed with the simple equations. They can also be even in algorithms, and or even also deep learning models. So I mean that the way how you compare two data points, this is this distance metric learning. This is really exciting kind of like a field of research. So the simple DBSCAN uses the epsilon constant, and the epsilon constant is actually that radius. So this is a radius that you would look over some of the, if you want to now calculate the distance between, let's say, and A and B, I don't know, wherever. So that there would be there that you would draw a radius around the point A, and then collect all of the points that drop inside that radius. And around each of those points, you use that same hyperparameter epsilon, draw a radius, collect all of the samples again, and do this as many times as needed. And then you calculate what is the longest distance between the last point you added and the target point. So the target point is A. The last point you added here is the B, and another side C. So to the B there is a like quite long distance here, and you just added that by some kind of expansion, like iterative expansion, using that epsilon constants. And this guy did not reach in that cluster, I mean in that radius, and that's why this is not included. And often those end up as being noise because they're probably not included in any of those overlapping expansions. And again, this is iterative way how you just calculate the distance metric between 2 points using, again, the hyperparameter, in this case the epsilon constant of that radius. And the first one was using just the number of k closest neighbors, and then calculate that distance. You're like, this is a little bit other way around. And here in this case, you have some arbitrary hyperparameter distance that you use to calculate, again, the neighbors. So we covered the first thing, that these clustering algorithms of HDBSCAN and DBSCAN, and I think optics also work the same way. They do not use classic Euclidean cosine distances. They use these kind of metric algorithms. So the points in the algorithm A and B, there's a question, are they random? So they are. So we need to know the distance through almost, or I think like you will see just in a second. I think you need the distance between every point in your data set, because you need to cluster them in some way. So I mean, like there are some algorithms that will do this like a little bit faster, and do not do the full search of all of the combinations, like the full factorial, but we will get to that. But in general, like to cluster, so if we go back to the first slide, to cluster these guys together, you need to know these pairwise distances between almost every of those points. So there are some optimizations we'll look at in a second, but it's not like you just randomly choose like the points and then cluster, then calculate the distances. To have these nice clusters, you need to know almost like all of the distances between the points. And these distance metrics that I just showed you, those are really nice to estimate the density. Like I don't want to cluster just like the similar distances of the points. I want that there is a cluster of sparse points, and then there is cluster of tight points. So that is the first point. So how the HDB work, HDB scan algorithm. So I'll go. So there are the points how it works. So the first one, I think in the blog or in those papers, it was not written in precisely in this way, but at least for me, it makes sense. So the first one is that you have the algorithm for calculating the mutual reachability distance metric. So that's the first thing. So that is that small algorithm to calculate the distance metrics. So then the next step to do that clustering is to do the minimal spanning tree. And you can do that in, I think that in that algorithm, they use not really classical way. So there is a classical way using, I think it's called Prim's algorithm. Again, that is problem that is covered a lot in mathematical papers for very long, like already, I don't know, that we can check what was the year when the Prim's algorithm was invented, 1930. So it was like really long time ago. So it's like, so 90 years ago. So anyways, so the Prim's algorithm is one. I will just in a second show what it is actually, the minimal spanning tree. So that is one, but they use actually the Brovka algorithm. So there is another one, dual tree. There are a lot of them. This is not only those, but there are others as well. So the Prim's algorithm would look at every combination and add them iteratively, even like I think you can make it in a recursive manner. And the output is this kind of nice picture where you have the minimal distances between every point in data set. Again, if we would do this just with the Euclidean distances, I think last time I explained that if we build this kind of tree with just using Euclidean distances, then any kind of noise would make this really terrible. So if you can imagine, there is some unfortunate point here in the middle, so it would not make a nice separation between those clusters, if you will, because there is some noisy data point. So they are kind of prone to the noise, but again, there is actually not the Euclidean distances between these minimal distances, but we use this mutual reachability distance metric, this algorithm that produces not Euclidean distances, but some arbitrary distances. So all of these lines that you see here, they are the distances, but they are not Euclidean distances. They are calculated by the algorithm that we just covered before. And in that way, we create nice kind of separation, even if there is a little bit of noise. Of course, if there is too much noise, there's probably, they will still not work. So that's one. Then let me check what's on my notes. Then the next one, I think, is to convert it to some kind of other way. So that will be the dendrogram type of the representation, and actually the clustering itself also happens through they call it, I think, condensed tree. This very similar to dendrograms, and I will just in a second show you. So let's keep the fourth slide as a summary of the algorithm. So then there is this dendrogram tree. So this is just another representation of the minimal spanning tree. Just a second, I will show you. And then the next one will be the condensed. And there is another really nice algorithm there in that condensed version. That will show you in a second. Condensed, what is the name of that? Con condensed tree, I think. Maybe I'm mistaken, but I hope condensed tree. And the condensed tree determines the automatic clustering. So the dendrogram tree, you can convert the minimal spanning tree from that. There is an example how it works. So it is like this. Where is my notes? Just a second. Copy. Okay, it did not copy from my Evernote, unfortunately. I don't know why. Trying to open my image. Just a second. Make sure that I can open it. Let's see. Okay, now it should work in just a second. So there, imagine if there is such a situation of the clusters, and we can represent that with the minimal spanning tree as in previous slide, or we can use the dendrogram. And then if you use the dendrogram, then the representation looks like this. And of course, you can like transpose the dendrogram to any axis you want. In this case, this is like rows are here. So I think these images really nicely represent how it works. So there are the indexes of data points, and then the indexes are also here. And then there is the similarity or the distance metric between those points. So what there is one key thing that I think is not immediately understandable is that if you look here, then there is a sample one. It's also here, sample one, sample three. Those are the pair where it's like the closest ones. And the distance between those two guys is here. Let's say if this is a two, there is, let's say, one. So this could be 0.8 or something. So this is those two guys distance, right? And when we have those two paired together, we can calculate the average between those. Like if we look here, is 1 and 3 point. We calculate average between them, put here another point in like in it imaginally, and then look what is the closest to that point. And if you look, the closest to that point is number 2. So the distance between that and that, there is like a small distance here. And then we calculate again the average between those 3 points, and then what is the closest to that one, and so on. Hopefully that makes sense. And you can draw this kind of nice picture where you already see the clusters basically. I think the DBSCAN algorithm at this point just have another hyperparameter where they just cut it like arbitrarily. You say, I want to cut it at this distance, so get some clusters out of there, or at other distance, and that's it. But the HDBSCAN is a little bit smarter, and the way how it is actually smarter is really nice. So just a second, if you go back here, and if I copy that image from that documentation, I think the documentation is excellent. The guys who made it did a really good job. So here, this is again the same dendrogram, just pivoted a little bit. Also, there are additional cool features here. So you see there is a color diagram here. It says that number of points. So it means that the more yellow is this color here, the more points it includes. So here there are the separate points, there are distances in between each of them, then the distances between like pairs of them, then the small clusters, then we go up, and at the end there is just one kind of distance between the two main like the one sample here and all other things, and there is this part. And I think also in this case the width here also is kind of measurement of, oh no, in this case, I think not, just the color. So the color means how many samples are included. The more yellow, the more samples are included. And of course, you can see why, because there are, in the very beginning, there are many samples, and then we combine them. So this kind of representation is just the same thing as the minimal spanning tree, but now represented in this dendrogram format. And then they kind of, I think they, when they invented the algorithm, they went in that kind of direction where they used the converted basically the dendrogram to condensed tree, and that condensed tree is the key for the clustering. So the condensed tree itself looks something like this, but I need to explain it a little bit, probably because it's some ways it looks understandable and others not so. So first of all, let's start step by step. So the again, the chart with the more yellow means more samples included. So that's great. There is a here the lambda value, which is really confusing. And I know, like, I understand that it's great that you have from 0 to 8 some kind of scale, but that is not really I think immediately understandable. And like, I'm not sure like if it really matters to have that kind of scale, because what it is actually, it's very simple. So the lambda is 1 divided by threshold distance. So threshold distance. So the lambda itself is basically threshold, and the threshold distance is any distance using that metric that we talked in very beginning. This is again not Euclidean metric, but this arbitrary metric that determines at which point we start clustering together something and consider this a new cluster or previous cluster. So if I think about in this way, I would like to rewrite it a little bit to make it more understandable, at least in my mind. Maybe that is just in my mind. So if it's just in my mind, really sorry, then I would try to help you out if then need to write some questions. So threshold here on the y-axis, this will be threshold, and in let's color this a little bit. So in the top part, if we think about 1 divided by something, this means that in the top part there is very large threshold. So all of the samples that are in the 10,000 or something like this radius, or whatever as you think, this is not exactly radius, but because there is a minimal spanning tree, but anything inside that distance is included just in one huge cluster. That's why there's a yellow huge cluster. And then if we go down, then at 3 there is 0.3, probably something like that. Then there is 0.2 at 5, I think, and then the threshold becomes even smaller, and then at 8 it's 0.125, I guess. So I think if the metric would be like if the scale would be in this way, then it's immediately a little bit more understandable. And the way how then it works is that we're trying to kind of sum together and integrate, if you will, to say the number of samples in those clusters. So we'll go just in a second a little bit more about this. I think the formula that they display looks something like this, where you have the sum of the samples included in the cluster with regards to first threshold, the last threshold, and the birth threshold. I mean the threshold at which the cluster appeared. So here the idea is the following, that like if we look at this dendrogram here, and if we just take a huge distance right here at this place, then it means that everything is just in one cluster, right? If everything is just in one cluster, then we add here like all of our samples in a like in a width. So there is a color and width. So the number of samples means this is actually a visual representation of the algorithm that is also quite fun, is the width and also the color and color. So they made it in a two ways, but basically it's a width. So the width is also great because if you think about the width, and you see those nice kind of bell shapes now here, the spikes, it kind of resembles probability distributions a little bit. If you put all of this together, like if you like glue all of those elements together, there will be nice few like few mountains, right, of the probability distributions. But in general, this is just a visual representation. In the actual code, probably you would not use this kind of representation. So the number of samples is the width. So what I mean, if I go again here, is that at the distance 8, for example, or 10,000 or whatever, we add the one line here, and this line is this width of that yellow box. Then we go to number 1, or let's say there is a what it could be then. So there's a 1, so the distance 1. So at distance 1, again, there would be another line, right? There is another line, another line. So you go by some arbitrary threshold step, like just like an integration, right? With the small step, go step by step and increase the threshold. Every time you increase the threshold, you log here as a line, horizontal line, all of the samples that you got. And then at some distance, suddenly, if we look here at this distance here, then there is at, let's say, somewhere here, we have two clusters now, not one cluster. And now we have two clusters also here. And then we add one line of how many samples we have on this side, and one line how many samples we have on this side. Then we increase again log those places. And then really fun thing starts. The lower you go with the smaller threshold, these kind of lines become like shorter and shorter, because less and less samples get into that distance range. And at the end, basically, you have some like kind of area. So what you calculate then at the end is the like integration, or kind of like sum of all of those lines, or the area of these spikes or these boxes, or basically what you call them as clusters. And you apply a really clever method, is that you would start looking at the you would start looking at I think you start looking from the last to the previous ones. And the way how you do this is, I think so we would color this a little bit. So you start with this one, you calculate what is the area of this guy. And this is probably a cluster, like really solid cluster, because the area of this one is much larger than area of this one. And it means that probably this is a separate cluster, and we take that as a cluster. Of course, the last one covers almost everything, and there is a specific parameter actually in this algorithm where you say, if you want to allow that everything collapse down to one cluster. In some cases, maybe that's okay, but like in most cases, you don't want that everything collapse to the largest box of the samples. So in some cases where you have like this density is like probably, let me think. So the density should be quite dense, I guess, and quite a lot of samples. Then in that case, maybe this first cluster would be like huge area that would surpass that yellow one. But in this case, this is not the case. So, but still, if we sum together all of those lines here, vertical lines, we get a area that is bigger than this green one. That is quite amazing, because if you look at the color, each of those lines is just smaller than that green one. But if we sum all of them together, they are bigger. So, and the same thing all happens also with these guys. So there is another cluster. So we have two clusters identified here. Then with these guys, this is different story. These are really small ones, and the next one in the range is bigger one. So it means that these two small ones are not clusters. And then if you look at this one and this one, again, this one is bigger again. So probably this is a cluster, and we would then stick that here we have three clusters, and we automatically got it by kind of simulating the kind of, I would like to say a time dimension, but actually simulating like this threshold and accumulating how many samples we have at each threshold with small like increments, and then sum together to calculate what is the area of those dendrogram like kind of branches. And in that way we can get the automatically the number of clusters just by using the density. So in this case we have three clusters identified, three clusters. I hope this makes sense. Maybe you could go over that documentation and look a little bit again. But if we go back here, so the first of all, unique mutual reachability distance metric or algorithm to calculate distance between two data points, not using Euclidean cosine or whatever, like Mohanobis distance, or there are a lot of kind of distances that are more mathematical, not algorithmic. These are a little bit algorithmic, actually. Then the minimal spanning tree, where we use that distance from the point one. Then we construct the dendrogram. Then we condense the dendrogram using that algorithm that I just showed you, where we increase the threshold of dendrogram and start calculating what are the number of samples that fall into that threshold. And in that way, we generate those clusters. So that's great. The last thing missing here, actually, there are two cool things missing here. So the one is, first of all, this method of summing together samples of dendrograms, they call it the excess of mass method. But there is also the leaf method that they did not describe in that paper, but there should in that documentation. But they say that that method is very similar in the performance that like this one. I think this one is really smart. Like it's kind of clever way how to automatically estimate the cluster number of clusters. Just to give you a reference, there are also some other methods to do this. Maybe I should drop those in the first slide so you so they don't mess with other things. There is a DBSCAN, HDBSCAN. The DBSCAN is basically without those two last points, because they already have the hyperparameter at which to cut the dendrograms, right? If you have the dendrogram, well, okay, that's without the last point. So then we don't need to have that last condensed tree. So the other options that you could explore is X means, G means. So all of these work without the number of so you don't need to know the number of clusters. Do not need to know k number of clusters. Almost all other methods need to know how many clusters you have. So this is quite cool. And so the missing parts. So the sum of the missing parts is, first of all, there is one called what was it called? Minimal cluster size. So the minimal cluster size, I guess you can also look at it here probably. So it kind of tries to eliminate noisy clusters. So for example, you have a lot of like edgy, like kind of non-smooth, like kind of fuzzy clusters. And to eliminate fuzzy clusters, they have this min cluster size where they would just then probably drop those as a noise. So even before starting to, so that's an important thing. I don't have time like to just like draw another diagram here, but the idea is that even before this condensing of tree, they filtrate out, so they delete all of these nodes that are with the minimal, under the minimal cluster size. So in this image, actually, this small box here means that it was above the minimal cluster size. Everything below minimal cluster size is cut off. That's why so nicely there are not so many like leaves at the end, because here if you look at dendrogram, we have a lot of small leaves at the end. So maybe you should add actually additional point here to filtrate out the minimum the minimal number of clusters after the dendrogram. So maybe I add here filter minimal cluster size. And this algorithm, as you saw in the very beginning, it also detects the noise. Kind of course, you can have also some kind of like how much which of the clusters is the more likely to be associated with this data point of noise. There is this kind of probability metric that you also can get, but in general, automatically it tries to eliminate noisy points. So the minimal cluster size. And the last thing that's also missing here is there is the option to enable DBSCAN method. So what I mean by that, there is really nice example, the kind of case study. I will try to find, where was it? There was in their own this documentation. This case study, I will quickly find it, where they show how to use epsilon. Okay, that was the way. The epsilon, just to remind you, is in the slide number 3, I think. Yeah, so that was the previous method, not HDBSCAN, but DBSCAN, where you just use that. This metric worked with the predefined epsilon radius, and then you kind of like propagate that radius where it overlaps with other samples. If you think about it, this algorithm is really nice because it kind of, if you know the epsilon, so you say that my data set is in this density and everything else that is not in this density is noise. So then it kind of really nicely clusters together all of the things of similar density. Everything that is like sparsely like a broad, they would be dropped. And there is a like algorithm, there is a parameter here. The parameter name, just a second, is the what is the name? Cluster selection epsilon, that you can combine with the HDBSCAN algorithm. The authors kind of have the way to combine both of these methods, because none of them are alone like perfect. So maybe I should just quickly, I will open that link here. I will also add that link, or you can just find it in documentation of the HDBSCAN here, where it gives really nice example why this is important. So here again, beautiful example how to use classical kind of clustering methods without deep learning to solve really complex situations. So there is an image of like the data points of people in the kind of like on the map in different areas, and you want to know in what clusters they group together, or maybe, yeah, I think there are people, but I'm not sure what was the oh no, those are the, yeah, big drop-off locations of customers of the ride pooling or something. So I guess there is like a parking space here. So you want to kind of estimate in which places you want to put like parking, for example, or something. So you have this data, and then you apply the HDB. So you like apply the DBSCAN and say, my epsilon that I just show you is 5 meters, right? And I propagate all of the samples that are in the 5 meters as the same cluster. And we got first issue here. So we see that a lot of points are gray in the background. You see there is a lot of more points here, and here is a lot of less. So it automatically thinks that everything that is sparse, that means that all of the sparse things are not clusters, but maybe there are like places where people drop off, but there's a little bit of sparsity. They are not always at the exact same place. So, and also this large blob here is not separated. Maybe it's okay, but you can see that there is actually three kind of parts most likely. And the DBSCAN with just using that epsilon is not doing the job. Plus, also you need to like do the grid search to find the correct epsilon for all of those situations. So then if you do the HDB scan, then the situation is much worse. So you think it solved the situation that these small sparse clusters now are covered. So it discovered more like good clusters around that big one in the middle, but the big one in the middle is again containing different kind of densities. So it's not really super uniform, and there's a lot of data points, and the algorithm thinks that there are like multiple types of densities inside that big blob, and the only way how to solve it is kind of combine both of those algorithms, and then you use the like your own predefined epsilon on top of already calculated HDB scan. And then when you do that predefined epsilon, you can eliminate the problem with the big cluster and still keep the sparse clusters. So the epsilon method will work only on the areas that are split in many sub clusters. If there are already this situation with sparse clusters, the epsilon method will say that there is kind of no clusters and they will not touch it. But in this case, where it's really nicely propagates through the whole big cluster, it automatically adds everything there. So I hope that I was in talking quite a lot about this, but I hope it makes sense. I hope you see that how cool it is. And so in my experience, the HDB scan is something that I use quite often, and the DB scan to estimate the number of clusters. So sometimes even you don't need to have the actual clustering like to done like what is the real clusters, but just it's always just enough to estimate how many there are. That also is useful. And yeah, so let's do a little bit of coding. I will not keep you too long, and then I will drop in Jamboard also these few samples of the code. The next time my plan is to return to the deep metric learning to that contrastive loss example, and I want to combine our contrastive loss example with everything that we covered so far. I want to combine it with the principal component. I want to combine it with spectra clustering, and I want to combine it with HDB scan. And in the end, we would have this kind of this metric that is coming out from our model can be used in classical clustering algorithms at the end to have the classification. So that's really interesting kind of progression that is often actually used in deep learning also nowadays, where this first line that we just covered with this algorithm that calculates the metric using this density function, you can also replace it with deep metric. So let me go to the code. So yeah, I didn't had unfortunately time to prepare a proper template today, but I will probably drop the template after the session in the Google Classroom, so you don't need to. So if there's something not working, so you can double check it. Also, I will probably try to make this example of image segmentation. So I like that idea a lot, that you can use the simple clustering for so many things, basically. So let's look at some very basic data sets. So first of all, let's say import sklearn. Oh, by the way, I'm not sharing or am I sharing? Yeah, so I'm sharing the correct screen. So datasets, sklearn datasets, that will be the dataset. Then of course import matplotlib, pyplot as plt, and then then Okay, zoom. Then we also will use the HDBSCAN, and you can install it by pip install HDBSCAN, and they updated it actually quite recently. So if by any chance you already install it, so you can add it as update flag here. And the terminal is here. In the terminal, you can just type it in here, pip install HDBSCAN, and install it with a nice PyCharm option where you can just open the terminal of the current environment. So that's why it's also nice to use it. Okay, I see that the question is, when will the homeworks graded? Yeah, probably you also are under pressure of the university staff right now. I'm leading some of the courses on the universities, multiple. So I think I will get on top of this course as well, and like the reason for this course is actually to at the end to work on commercial and scientific research, like probably with the paid position. So anyways, like you should not be that worried about grading. You just need to submit those works, and I will give feedback definitely, because you are the few guys that I actually, and girls that I would like to work in the future as well. So don't worry about that. But yeah, thanks for letting me know. So the sklearn datasets, matplotlib, HDBSCAN, and the things that we are just right now covering. I'm specifically designing this course in in the direction of deep metric learning, because in ASIA research and also in some of the university research, we're working with deep metric learning specifically, and this area requires this kind of knowledge regards to the dimension decomposition, reduction, and the clustering and stuff. So here, okay, we have the sklearn datasets, load, what was the load iris, for example, return, uh, my autocomplete is not working, unfortunately, again. True. Hopefully it will work. XY. So what I'm loading here is the famous iris dataset that my students remember from very beginning, probably when we started working with you. So that is just like classifying some pretty flowers of 4-dimensional. So yeah, you see the inputs is 500, I mean 150 flowers with 4-dimensional parameters, like the lengths of the leaves, right? And then there are 3 classes in the vector. And if we plot it, so first of all, this is a 4-dimensional data set. We cannot plot it just immediately. We need to use PCA. So there are other dimension reduction as well that you could use, but that is not linear. So we would like to use something that's linear to not fool ourselves. So to have like the like, if you use the simple linear principal component analysis, that means that you basically have the closest way to look what is the actual metric between those samples. Like all other methods kind of apply some non-linearity that could be useful for the classification, but it would not give the measurement of how good is your like raw metric that is feeding into this yeah, to the PCA. So I mean the X itself, in this case, this is data, but of course from the deep metric learning, we would pass X through our encoder, and then we will get some embeddings, and those embeddings would be our real metrics. So here, and then we want some kind of PCA linear method to estimate how good are the metrics. We want these metrics to work probably in Euclidean space, maybe in cosine space, or something like L2 normed space, or unit space, or something like that, where we visually can see how good they are. And if we would use kernel PCA, that is great for classification, but not so great for like kind of pure visualization of how good is our model. I hope that makes sense. Maybe when we will start working with it, you'll have more sense of it. So there is a XP projected one, right? We already made step by step our own PCA, if you remember. So there will be the fit transform of X. And then I want to plot it. So I actually want to plot it in two parts. So there will be a figure, and the fig size will be like a A4 format or something like that. So there will be plot of subplot of 2 rows, 1 column. This will be first one. Then there will be plot scatter, and the scatter, of course, will contain this dimensionality. So there will be the first one and the second one. I cannot really here display the row X because row X contains 4 dimensions. Now we have 2 dimensions here. So that's great. And the colors will come from ground truth. In the top will be ground truth. So if I write here title ground truth, right? And the C map, let's make it rainbow. I discovered that this looks great. Rainbow. Maybe there are some other. I think the grays are also good in sense when sometimes. So okay, this will be fine. So I will copy these lines, and also have the same for the clustered or the predicted. Basically, if you have the assignment of the clusters, you can treat that as a prediction, and then you can basically calculate the accuracy even or anything. So the accuracy also can be then calculated. So PLT show. So we'll see this one. So I will close. So it should look something like this. I experimented before this session. So let's see if it looks like that. And the Y here is not actually the predicted one. We will just produce the predicted one in a second. So if I run it, okay, now it shows something. Okay, so it shows something like this. So we have 3 clusters. These 2 are not separated well, and also the separated well, they are not separated well, and also the density looks the same. So they probably will not be great fit for this algorithm, but still we'll try. So clusterer or just clustering algorithm, let's call it like that. There will be the HDBSCAN, and that will be the HDBSCAN. And here there are the main parameters that we are just discussed. So first main parameter, of course, min samples. So the neighborhood of minimal samples that is used for the metric, right? So the metric, what was the name of the metric again? There are so many names for them. Mutual reachability distance metric, or also they have the core distance basically. So this will be, let's say there's 150 samples. You look here, there are, let's say, it looks about 3 samples, or yeah, about 3 samples. Maybe that would be a good closest 3 samples or 2 samples. So this is for distance metric. This is that mutual reachability metric that we just discussed, where there is maximum of the Euclidean or those k closest samples. So that is the first important parameter. Then the next important parameter is mean cluster size. So that is what we want to drop. In this case, it looks like that maybe if you're honest, that those points on the sides here, they're not really that good candidates for clustering. They probably would be treated as noise. So it looks like, but there is actually not so many clustered together, I don't know, let's say let's say if there is something like 2, then we drop, but in all others we include. So that's one. And then the last metric is the, what was the cluster, no, the last metric name, we discussed it where we with that DBSCAN, cluster epsilon, right? Cluster epsilon, right? By default it's 0, I think. So it includes, so I think not includes, but 0 just ignores that method, I think. So let me see. Yeah, 0. So, and if the result will not be good, then we can, depending on how it's not good, like if we see that example where, with that like drop off of the people in the map, where we see that there are a lot of small clusters that we want to join them together, then maybe it's a good idea to use this algorithm, this also parameter. And then there is actually also another parameter, alpha, that is usually better not to touch. The alpha is, if I understand correctly, it's a part of the minimal spanning tree algorithm that have a huge significant effect of the performance. I think the alpha is kind of some of the parameter depending on how good is the minimal spanning tree result. I think it like if you tune it, you can get it more detailed or less detailed, but at the same time, it's kind of dangerous to play with the completely two different big algorithms. One is for minimal spanning tree, another one is for clustering. So better not touch that one. So that's one. Then Y prim here will be the labels, basically the to which cluster it belongs, right? So fit predict, and here's important, we are predicting or the clustering the real data points X here because there's a low dimensionality, there's dim4, right? If by any chance there would be dimensionality of 128 or 256, we see here we have Euclidean metric as a third part of that formula for mutual reachability. That means that maybe for high dimensional datasets we should use here XP, but in this case X is good, and actually it's better than XP because XP here is reduce dimensionality, lose information. So here we don't want to lose information, at least for that dimensions. So if I run it, I will also drop this in Jamboard if it works. So I get nice 2 clusters. I don't get 3 clusters. That's not great. Maybe we can do something. So the minimal cluster size will not help. What could help is the minimal samples. So there is a counterintuitive thing. You would think that if you reduce that number, it would work better. But if you look here, there's some of those samples are quite far apart and they are not really clustered in the same density. So maybe even increasing the number could have like better effect. So let's see. So if I increase it, I get a little bit noise also here now. So it's dropping the sides here, but it's still not splitting it completely. So unfortunately, not, probably with this method, it would not really work. But to be honest, like the data itself, it's not that clean to begin with. So the way how this should be then solved probably is if we would use our, for example, deep metric learning model to first have much cleaner metrics. So the metric where there is not so much overlap between those 2 classes. And if there is not so much overlap, then we can have nice 3 clusters. So what I mean is to create a model that would create embeddings for those. So that's one approach. So I'm dropping this in the slide 7. I will think also some other data set to give you as a homework to work with the HDBSCAN. Probably that would be fun. I will prepare a template for the homework to do the image segmentation with this method. So just before ending today, let's look at another really fun example. So we need to change only this line here. We can load in like predecessor of MNIST text dataset. If you remember MNIST dataset, right? It is that image dataset where you need to recognize the digits, like the numbers on the images. So there is a similar dataset in the sklearn. It's called digits. I think it was 8 by 8 the size. Or I think it was 8 by 8 size. But again, we can use the raw image, and even if we pass it to the PCA, it would be even first kind of type of idea of the metric learning, because then we could project it on a little bit better metrics. So let's see, there is a Y shape. What is the shape? Yeah, it's 8 by 8, and there are almost 2,000 samples. So it is 8 by 8 images, and then they are flattened. They are flattened to the 64 dimensions, right? So the 64 dimensions is not that bad, actually. So the 64 dimensions probably would work well also with any kind of clustering, probably. Just a second, let me check where there is a chat if you write something. I somewhere lost my chat window. Sorry for that. If you're writing something, I cannot find it anymore, but I don't want to waste time here. So anyway, so this is digits. We can even plot it visually, but I don't have time right now. But we can plot it visually with, if you want to look at how it looks like, you can use plot image show, and then you can, of course, you need to reshape it to 8 by 8 when you can see how these images look like. So and then if I pass it through the same method that we just have, just change the data set, maybe we will see something nice. So so the original data set looks like that, with plotted in 2 dimensions with a PCA reduction. So there's different letters, or basically numbers. I think there should be 10 at the end, so we can check actually what it was and what we got. So the way how to do that is the following. So we can write print the Y labels, and this can be got by NP unique. Oh man, I did not include numpy. Import. You should always include numpy, even if you work PyTorch or other. Unique, right? So the unique is basically the same as doing the list and then the set of the Python. So there will be Y labels. So these will be the how many labels are unique here and how many labels are unique here. And also I would like to actually calculate, not to list them, but calculate how many there are. So I use the len. And I will also give in a comment what it is actually. So the idea what it is just to have the to list, then cast to set, right? So basically you could have the same output can be applied, get like this, Y to list set and that. So if you know in the Python sets, so this is the same idea. And if I run it, only the unique function actually can give you back also additional information that is sometimes useful. So we have the original is like in MNIST 10 digits, and the predicted now is really bad, 126 classes. So to solve this, we can improve. So first of all, we know there are like almost 2,000 samples, so that means the minimal cluster size will definitely not be 2. So let's say the minimal cluster size maybe is 100 at least. And we don't know how balanced is the data set. Maybe it's actually balanced, but maybe not. So here is now there is a 6 sample prediction. But this is not optimal as well. So maybe 20, this could be fine. Let's reduce it now to 50. Again, you start seeing that, again, this is a hyperparameter search. Unfortunately, for these models, again, you need for the clustering, even for the clustering, you need to do the hyperparameter search. And to do the search, you need first to pre-train really well metric. So in this case, the metric inside the HDBSCAN is this one that we just talked about, mutual reachability metric. This can be also replaced by our own metric. If you look here inside, there is a called, I think there's a metric, and you can change, if you change this metric to pre-computed, you can load in here your own metric. So it's not like not something that we calculate with those nice radiuses and the max function, but maybe invent your own, or have the deep learning to invent the metric. So that's quite a cool idea. I mean, and then you calculate the distance matrix and pass it as a pre-computed one, and you got it working. So let's look at this one more time. So the minimal cluster size of, okay, now we got 9. What I would like to see is a little bit more than 10, and then reduce it using the epsilon method. That will be great. So okay, with the 10, it's perfect. So, but at the same time, here it's not actually perfect, because some of the clusters actually match and others do not match. You can see there is definitely something going on. Also, probably there is a noise included in those. If we look what I got here in Y prime, I bet there is noise as well. So the noise is -1 actually. So let's see. Yeah, we have actually okay, there's a -1s multiple times. That's interesting. That's interesting. I was not expecting to see this. Okay, let's check out my method that I showed before. Okay, no, that works. It's just strange output. Okay, I know where the problem is. I was not using the unique method here. I wanted to use the unique. So if I run the unique, then I will get actually the unique samples. Yes. So -1 noise, 0, 1, 2, 3, 4, up till 8. So that means there is one cluster that is noise actually. So if I increase here to 20, I think there was a little bit more. So this is 9. Okay, no, sorry, it didn't need to do that. Let's say so 5. Minimal cluster size. So 19, now I have 19. So probably that blue one is considered as noise, so that's not optimal. Anyway, the other way how to estimate which should be the best parameters here is to actually calculate the accuracy. So if I have Y prime here and we had a Y, you already know how to calculate accuracy. So the accuracy would be one guiding principle. There are other methods as well. So I need to end for today. I will drop this code also to the Jamboard, to the last slide. So please play around with this one, and I will prepare template for you to do the image clustering using the image segmentation using the clustering algorithms. I think that's really fun approach. So, and also useful for thinking about how all of this stuff works. So in general, that's it for today. Next time we will work with the, okay, I found the chat as well. Next time we're going to work with the deep metric learning again. We will start putting the things that we just learned with the classical data processing and put it in the context of deep learning. And then we work with the triplet loss and all sorts of other more advanced like metric learnings. So I hope this is interesting. I hope it kind of opens your mind about thinking what you can do with the machine learning and with the classical algorithms. And there's a lot of things that you can still invent and research your own. So that's it for today. Bye-bye.